Over the course of the next two videos, we'll be talking about the different models of the atom and the history and experiments that led to each of these discoveries. In this first video, we're going to go over older atomic theory, which is up until around 1900-ish. In the next video, we're going to cover the two newest models of the atom that are both currently in use today for different reasons. You are going to need a notebook or your fill-in note sheet. You're also going to need something to write with. And once you have all those ready, let's go. Before I actually get into atomic theory, though, what I want to go over a little bit is the idea of the scientific model. When I say model, what comes to mind? Right? So a lot of you are probably thinking like, well, model cars, model rockets, like all of these things that you can build that are tinier versions. And that's, for us, kind of the same thing. A model for us is a visual representation of a system. What it does is it shows the important parts of that system, how the system functions, and it can also show how the different parts of the system interrelate to each other. Right? So if we think about, for example, the planetary model, you have the sun in the center, you have the 8 planets going out, some of those planets have moons, right? You can draw the or you can draw the individual bodies to their relevant sizes, at least proportionally scaled, right? Because planets are really, really large, so we want to scale them down. And you can get a good working model and see how everything works. For our case, especially in atomic theory, it's going to work the same way, but because atoms are really, really small, we're going to just scale them up a lot. Now, in order to create a model, we have to collect significant amounts of data, right? So all of these, or I shouldn't say all, but most of these are research-based, based on the experiments that these scientists have done, and then they took those experiments results and figured out what that meant for the structure of the atom. Now, one of the important things about a scientific model is that when we come out with new evidence that disagrees with our model, that's not a bug, it's a feature. What we do is we alter the model to account for the new information. So what you're going to see as we move through atomic models is that they all start on the same basic place, but then as we make a new discovery, we make a change to the model that we were working with to account for this new information. All right, so the first model I want to work with, and this is the only non-scientific model of the atom, is based on a thought experiment. Right, so this is Democritus, who is a Greek philosopher about 400 years BC, or BCE, depending on your preference. And he had this idea, well, what if I took a sample? He used gold, but I'll use aluminum foil because it's easier for us to work with. What if we took a sheet of aluminum foil and we tore it in half? You'd have 2 sheets of aluminum foil that are half the size, right? Now, what if we tore those halves in half and kept tearing each half in half? What happens? Well, what he theorized was that if you get small enough, you eventually reach a point where you can't cut it in half anymore. Right? So that smallest point where it cannot be divided in half, he called atomos, which is the Greek word for indivisible. That's where we get the word atom from. Atoms are indivisible parts of an element. Right? So this is the first actual recorded use of the idea of the atom. So if we were to describe this in one word, I would just say that this is a concept. Now, do we use this model today? No, it's not very relevant to us because it doesn't provide us any useful information. But as we go forward, we'll move forward about 2,000 years, and we'll talk about the work of John Dalton. So this was 1790s, 1800-ish. So this is his atomic theory, right? The idea is that he came up with through his experiments using atmospheric gases, things like oxygen, nitrogen, carbon dioxide. Right, so his first tenet of the theory is that all elements are made up of particles called atoms. All atoms of a given element are exactly the same, but elements are different to each other. So all oxygen atoms are identical, but an oxygen atom and a nitrogen atom are 2 completely different things. You cannot break an atom up into any smaller piece during a chemical or physical process, right? So they're indivisible. And when you perform a chemical reaction, atoms will rearrange themselves in order to form new compounds. Remember, compounds are just combinations of two or more atoms, right? And his model, based off of this, is what's called the billiard ball model. Atoms are just solid spheres, right? There's nothing special going on with them. They're just a solid sphere, kind of like a pool ball. Each different ball is different from each other, right? So the cue ball is different than the 9 ball, is different than the 3 ball. And do we use this model today? Kind of. Like you've seen particle diagrams that we've drawn, right? Particle diagrams, we just draw solid circles or solid spheres, and we use those to form a quick comparison between things. So we kind of use it for that purpose, but as far as like scientific principles, it really doesn't go forward that much, but it got the ball rolling because this was the first one based on experimental evidence. Our second atomic model, this is J.J. Thomson, early 1900s, so 1904. What he did was he took what's called a cathode ray tube, right? So this giant tube that we have right here in the diagram on the right is called a cathode ray tube. If you guys remember CRTs, these are like if you've ever seen those old TVs or computer monitors that are like a foot deep, that's because they had cathode ray tubes. Modern monitors don't use this technology. The idea behind a cathode ray tube is that if you put electricity through the cathode ray, it produces a particle. Now, what Thomson recognized is that this particle is repelled by negative charges. So if it's repelled by negative charges, the particles coming out of this cathode ray tube also have to be negatively charged. Now, it doesn't matter what substance he used to make his cathode ray tube, whether it was copper or gold or steel or whatever else, it all worked exactly the same way. So every atom has to have these negatively charged particles, and he called these particles electrons. So this is the discovery of the electron, right? So if I were to use one word for this, it would be electron. Now, the model that he made off of this, again, we're going to take the previous model and make a modification. The previous model was you just had a solid sphere and there was nothing special about it. So what we're going to do now is we're going to modify that solid sphere a little bit and create what's called the plum pudding model. Plum pudding is a famous British dessert. If you guys want one that's a little bit more relevant for you, think either the chocolate chip cookie model or the Jell-O mold model. Right? The idea is the electrons, which are the negatively charged particles, sit inside of a quote-unquote billiard ball that is overall positively charged. So if we think about the chocolate chip cookie model, for example, the little chocolate chips are your negatively charged electrons, and the cookie that they're sitting inside is this positively charged stuff. Now, there's enough electrons and to exactly counterbalance the positive charge of the billiard ball in this case. All right, so this is a way to think about Thomson's model. Here we've discovered the electrons, and all we've done is just move the model forward a little bit to account for it. Now we'll move forward a couple more years to the work of Ernest Rutherford. Ernest Rutherford didn't like Thomson's billiard ball model, or didn't like Thomson's plum pudding model. He thought it was incorrect. So he set up an experiment to disprove Thomson's model. What he did was he took a very small piece of gold foil. The reason why he used gold is because gold was one of the densest elements you could get. And he was going to fire a beam of what are called alpha particles. Today we know them as helium nuclei at this gold foil. If Thomson's model were correct and most of the atom was just this positively charged stuff, what you would expect these very high-speed alpha particles to do is punch through with absolutely no resistance. right? So they should just go right through, straight line, no deflection, because they're traveling fast enough to just punch through the foil. Now, what he found out was something completely different. He noticed that there was a lot of deflection in some of these, right? So they bounced off to the sides. And even a few of them, right? So if we take that particle that we have at about 5 o'clock, that one bounced almost straight back. That shouldn't be possible under Thomson's model, right? Atoms should not bounce straight back. So we have to think and we have to modify this atomic structure to account for this. Well, if things bounced back, that means there has to be something in there. Now, alpha particles are positively charged. So we'll get to our model here. This is what's called the nuclear model. Alpha particles have a positive charge. So the things that are deflecting them in the gold foil also have to have a positive charge. Right? And since only a handful of them ever bounced any major degree, what we have to assume is that that positive charge is very small. Most things pass straight through, few bounce back. So very small positively charged thing, and then a lot of region that's just empty space. And this is where we came up with the idea for the nucleus. Now, the nuclear model of the atom is something you have seen before if you've watched any Saturday morning cartoons, right? It's just the Jimmy Neutron symbol. You have the nucleus in the center of the atom, and then you have the electrons orbiting the nucleus like a planet orbiting around the sun. So here, the one word that we would use to describe this is the nucleus. And do we use this model today? No. This model has been overcast by two other models that we'll talk about in the next video.